a ver la presentación de la línea de investigación de la profesora Isabel Correia. Tuvimos esta semana 3 jornadas de lo que fue el mini curso de Química Bioinorgánica y Metales en Medicina, que terminó ayer. Salió muy bien, les agradezco porque muchos de los que están acá también participaron en el curso. La profesora Isabel Correia es académica del Instituto Superior Técnico de la Universidad de Lisboa, en Portugal, y es investigadora del Centro de Química Estructural del instituto. Isabel es una investigadora que es reconocida internacionalmente en el campo de la química bioinorgánica. Tiene más de 120 publicaciones en revistas indexadas, principalmente investigaciones que se centran en química de coordinación y el uso de compuestos de vanadio, cobre, zinc, hierro, entre otros metales, como metalofármacos, es decir, compuestos inorgánicos que tienen aplicaciones en salud, tratamiento de enfermedades como el cáncer, por ejemplo. Isabel ha sido autora de 5 capítulos de libros, ha participado como speaker en más de 20 congresos internacionales, también ha participado en la organización de congresos, 4 congresos internacionales. Recientemente, a fin del año pasado, fue chair del simposio, del 13º Simposio Internacional de Vanadio, que se realizó en Portugal en octubre, noviembre, en esas fechas. Es miembro y ha sido miembro de varios proyectos de acción bilateral con distintos países de Europa, como España, Polonia, Hungría. También es miembro del comité editorial de los journals Frontiers in Chemical Biology y de Inorganics, y ha sido mentora de varios estudiantes de pregrado y de posgrado. Esta es la segunda vez que Isabel nos visita a Chile. El año pasado participó del congreso que organizamos junto con varios colegas de la Universidad de Santiago, el Encuentro Latinoamericano de Química Bioinorgánica, y eso permitió establecer este contacto, y también haciendo uso del convenio que tiene la Universidad de Santiago ahora, a partir del año 2020, la Universidad de Santiago tiene un convenio de cooperación internacional con el Instituto Técnico Superior de Lisboa y la Universidad de Lisboa. Así que hoy día Isabel nos va a mostrar qué es lo que es su línea de investigación, y al final de la presentación nos va a hablar sobre el instituto y cuáles son las potencialidades que tiene, exactamente cuáles son las potencialidades que tiene de ir de mantener esta colaboración. Así que eso, dejo a Isabel. Muchas gracias.
Muchas gracias,
Isabel.
Luis. So I'm going to switch to English. I would like to thank Usach for the opportunity to be here, to spend some time in this lovely country, meeting very nice people. So I must say that I'm in love with Chile. So today I'm going to speak about my research work, but I will start with an overview of where I come from. So I come from Lisbon. This is a picture of Lisbon. Some people say that it has some similarities with Valparaíso. I think it doesn't, but except for the hills. And this is a river. This is not the ocean, although we are very near the Atlantic Ocean. So it's a beautiful city. I invite you all to come. My university is the University of Lisbon. If you go to their website, it says that it was created somehow in 1219 when King Dom Dinis created the General Studies of Lisbon. Many other things happened along the years. In fact, the creation of the University of Lisbon was in 1911. We have around 50,000 students. These are numbers from 2021, in which in 2021, 11,000 were diplomated, got their diplomas. In fact, I work in the Instituto Superior Técnico. It's an institute that was also created in 1911. It has 1,000 students and around, 11,000 students and around 1,000 faculty and university researchers. So it's a very big institute. We have mostly engineering. It's an engineering school. It's considered one of the best engineering schools in Europe. We have all kinds of engineering: aeronautical, biomedical, chemical engineer, biological engineer, many different fields. 34 master programs and 33 PhD programs. We have 3 campuses. The main one is in Alameda, in the city center. This is where Sebastian Staffarelli spent 3 months in the end of the year. We have just inaugurated this building, which is a beautiful building. This used to be a guard for electrical buses, and it's now the Technical Institute for Innovation. And I think good things will happen here. We have 2 other campuses, one which is devoted to information and communication technologies, and ETN, in which it's mostly a research center for nuclear sciences as well as radiological protection and nuclear safety. So we have 3 different campus, the main one being in the city center. Then my research, I do it within a research center, which is Centro de Química Estrutural. It's the largest chemistry center in Portugal. It was founded in '75 by these 5 researchers. They are well known in their fields, particularly Professor Fraúcho da Silva. He died 2 years ago in the bioinorganic chemistry fields. Professor António Xavier in the molecular physics. He was responsible for creating ITQB, which is a research center from which many important Portuguese researchers and scholars came from. So this is the evolution of my research center. Currently, we have 11 groups in all different fields of chemistry. So if you want to collaborate with us, I think you can find some field in which our research fits. I am currently the coordinator of the Bioinorganic Chemistry and Drug Development Group. Just an overview, our research center has 4 thematic lines: synthesis, catalysis, and reactivity, materials, soft matter and nanochemistry, sustainable chemistry, and medicinal and biological chemistry for health. So I invite you to visit our website and to check if there is a match between our interests, because Chile and Portugal we are quite different in terms of size. I think we are around 1/10 of in terms of area. In terms of population, we have half the population. So I would say that in Chile, people are concentrated here. This is the demographics. In Portugal, we are more concentrated in the littoral also. And I was checking some data, and I found it interesting that we have some indicators which are more or less the same. Like the civil rights, the same indicators, cost of living, very similar, and popularity, although Chilean people are more popular than Portuguese, whatever that means, okay? So there is this protocol, this convenium between Usach and Técnico. This is the reason why I'm here. And so I invite you to take advantage of this collaboration and to come and visit Lisbon, okay? So I'm available for speaking more about my university, my research center, and what we do in there. But I will now move to the research work that I carry out in Lisbon. The title of my talk is Metal Complexes of 8-hydroxyquinoline Ligands, Structure, Solution, Speciation, and Anti-Cancer Potential. So some of you were this week in the course that I gave. So some of the aspects that I was highlighting during the course, I will mention them today. So I don't think I need to tell you how important cancer is in our society nowadays. It has a very high impact in terms of personal lives. All of us know somebody who had cancer or died from cancer. This is data from 2018 by the World Health Organization that predicted 18 million new cancer cases. So cancer, it's a group of very distinct diseases, and it is very important to develop new compounds to efficiently kill cancer cells and cure cancer, different types of cancer. Our aim in the project that I'm going to present here today is to develop new ligands and metal complexes, and the objective is to obtain stable and efficient and selective compounds. So selectivity is an important issue. We use analytical techniques, stability studies to evaluate our systems. Then we do, in collaboration, in vitro screening on human cancer cells. We try to evaluate and to establish which are the mechanisms of cell death that these compounds have. And in this project, the most active compounds were selected for encapsulation in nanoliposomes, which are shown here. And then in some systems, we did some in vivo studies with mice. And the objective is to select lead compounds to proceed for preclinical trials, okay? So our strategy is to use ligands, organic molecules that are already active by themselves. And in the last years, I've worked with phenanthroline, a very known molecule, and 8-hydroxyquinoline. These two types of ligands by themselves have cytotoxic properties. And then to complex them to transition metal ions, and I don't have a preference for a metal ion. Typically, we use iron, vanadium, nickel, copper, zinc, and sometimes even ruthenium. And the idea is to change the biological effects of the ligands and to aim for additive or ideally synergistic effects between the organic and the metal species. So why 8-hydroxyquinoline? It is considered a privileged structure in medicinal chemistry. And why? What does this mean? It means that this compound has a broad range of biological properties, from antibacterial, antiviral, anti-cancer, etc. And it is considered, and I've spoken a little bit about this in the course, that the anti-cancer activity is related to its ability to chelate metal ions and to take them inside the cells. Our strategy was not to simply use 8-hydroxyquinoline. There is a lot of work in this field with many different ions. It was to expand the chelation system by modification of the position C2 on the ligands. And of course, then to complex it to metal ions. So we start with this compound that has a methyl group here. We do an oxidation with selenium oxide to produce the aldehyde. And then with this aldehyde, we can react it with different amines or hydroxides to produce ligands which have a higher chelating ability. I will show you today some with more detail, some other systems more briefly. 3 different systems, one in which we synthesized one ligand and complexed it to a series of metal ions, vanadium-4, iron-3, nickel, copper, zinc, and ruthenium, although I'm going to focus on the zinc data that we obtained. Another system in which we obtained 8 different ligands with different substituents here in this para position, and as metal ions we chose vanadium-4 and copper-2, and this system which are Schiff bases in which we produced 5 ligands, although I'm going to focus on the ones containing morpholine and piperidine, and we complexed it to a series of metal ions. The work with copper and zinc has been published. This is what I'm going to show you, but we also have data that I will have no time to show you on the vanadium, iron, and nickel complexes that are right now being evaluated. So let's start with this ligand. It's a very simple molecule. We decided to couple the 8-hydroxyquinoline with this benzotiazole because this unit also shows some bioactivity. So it's a simple reaction, the formation of the ligand that we then characterize by the usual techniques, and something that we now try to do is to determine the protonation constants of the ligand. We do this by UV visible spectroscopy, in which we change the pH. We could not determine the pKa value for this proton here, but we could see that the first proton to go out is the one from the nitrogen quinoline, then the phenolates in the usual pH range, and in the end, this proton. The problem is that this ligand has a very high log D value, around 3, so it's very lipophilic. And neutral at physiological pH. This is the species that we will find in solutions at physiological pH. This ligand, as I told you, was complex to a series of different metal ions. We obtained 1-to-1 complexes and 1-to-2 metal-to-ligand complexes in the case of copper, nickel, and zinc. With some metal ions, we only obtained the 1-to-2 complexes, as with iron 3 and vanadium 4, regardless of the metal ratio that we used in the beginning. And for ruthenium, it was interesting because we started with a ruthenium 3 species, which was reduced, we believe it was by triethylenamine in the reaction system, and we obtained a ruthenium 2 compound. Of course, these are a lot of compounds. We were not able to obtain X-ray structures for this system. It's not easy to crystallize it. But we did a very extensive spectroscopic characterization of the system, EPR for copper, NMR for zinc and nickel, and also for ruthenium. The same for the 2-to-1 complexes, EPR for the copper and vanadium. And here I show you the spectra for the Zcl and Ning complexes, the 1H, the proton NMR spectra in the MSO. And we can see that the quinoline moiety does not bind the metal ion in these complexes. So this ligand seems to have a very versatile mode of coordination towards different metal ions, because different ratios and different metals bind this ligand through different binders. For instance, here I show you the spectra of the ligands, the zinc 1-to-1 and the zinc 1-to-2 complex. And we can identify here the proton corresponding to the phenolate in the ligands and in the zinc L2. In the case of this one, this is not the proton belonging to the phenolate, but the proton from the imine, which appears in this range. One thing that we always need to evaluate is what happens to the compounds when we put them in aqueous solution at physiological pH. Because, as I've said, the ligand is quite lipophilic. The complexes are also lipophilic, although we did not measure it experimentally. But what we typically observe is that at concentrations which are relevant for the biological studies, in the low micromolar range, we can see that within 24 hours, the compounds precipitate. However, when in the presence of bovine serum albumin, and when we do biological cytotoxicity studies, we always have the presence of a high amount of BSA, which is added to the cells in the form of fetal bovine serum, so for the cells to grow. And this protein is important in solubilizing the compounds. So in 1-to-1 mixtures containing our complexes and bovine serum albumin, you can see that the spectra change a little bit, probably due to binding of the complex to the protein, which is not such a fast process, but the compounds do not precipitate. We proceeded to do an anti-proliferative screening. So this project originally was intended to be applied in melanoma treatment, but we also tested for colon cancer, and we used 2 different types of cells, so the human variants and the murine variants. Why? Because we wanted to proceed to in vivo studies, if possible, and we use mice, and these are the cells that we use to model these cancers. So because we had a lot of compounds in our hands, we chose 2 concentrations and tested what happened with these concentrations. So in this table, you can see that most of the compounds will have IC50 values below 20 micromolar. But in some cases, for instance, for the zinc complexes, there seems to be a lower toxicity for normal cells, keratinocytes. So we decided to choose the zinc complexes to proceed because they seem to show some selectivity towards cancer cells. So for the zinc complexes, we determine the IC50 values. Indeed, they are below 20 micromolar for the tumor cells, but they do not show that much selectivity, okay? Which is common for this type of complexes. So with these things in hand, we decided to choose just one of the complexes, and we chose the zinc 1-to-1 ligand because it performs better in the murine tumor cells, and it has a lower molecular weight, which is always a good property for application in biological systems. So this compound is cytotoxic in the micromolar range. It has low solubility in aqueous media, non-selective toxicity towards cancer cells. So we decided to use a drug delivery device, and as drug delivery device, we chose nanoliposomes. What are nanoliposomes? They are nanocarriers, lipid-based, and it is considered that they have high biocompatibility, biodegradability, and low immunogenicity. And the good thing is that we can incorporate hydrophilic or hydrophobic molecules, and typically when we incorporate the drugs in these lipid systems, we protect the drug from degradation, enhancing its solubility and stability. So this is a drawing of a liposome. So hydrophilic drugs will be incorporated here. Hydrophobic drugs, like our complex, will probably be incorporated in the lipid bilayer. And typically we include PEG, it's a polymer, which increases the blood circulating time. The strategy was to take advantage of the enhanced permeability and retention effect, which is a process by which, so the vascular system of tumor environments are leaky, are deficient, because tumor cells need a lot of nutrients, so they grow their vascular system very fast, and typically there are defects which allow for the penetration and the accumulation of high molecular mass molecules, okay? So a small complex will accumulate in tumors and normal tissues because they have the same, they are able to permeate all the blood vases in normal and in tumor cells. High molecular mass compounds can only penetrate and permeate tumor tissues, and so they will enter the cell by endocytosis, and because the endosome has a lower pH value, they can be released from the liposome and then carry on its effect. We use different phospholipids. I'm not going to show you much about this slide. We characterized, of course, the liposomes in many different aspects. I also have no time to go into detail, but we evaluate the internalization efficiency, which of course should be high, the diameter, which should be below 200 nanometers, it's like the ideal size, the polydispersity, the zeta potential. And from this list of liposomes, we chose this one mainly because it had the highest incorporation efficiency. So now we had in our hands the free compound and the incorporated compound into the liposome. What we did was to test it to see if the liposomal formulation of the zinc complex was able to retain the cytotoxicity. And in fact, you can see here that for the human and for the murine colon cancer cells, the IC50 values of the complex in free form and in liposomal form was very similar. You have here the positive control that we use in this study, 5-fluorouracil, which also has a very low IC50 value in the colon cancer cell, the murine colon cancer cell. And so this was a positive result, because sometimes after incorporation, if the compound is not easily released from the liposome, it has no cytotoxicity. So in this case, the result was what we were aiming for. So we proceeded to do in vivo studies. So we used the syngeneic murine colon cancer model in which we grew the tumor in mice. Then we took the cells, the tumor cells from the mice. They were grown in vitro, and then they were implanted in mice from the same inbred strain. Just a few details on how these in vivo studies were done. The tumor induction was done by subcutaneous injection. Then the treatment was initiated after 13 days when the tumor was visible, palpable. And then we initiated the treatment. We divided the mice in 5 groups with 6 animals per group. And they received daily IV injections of the formulations. So we had 2 negative control groups, mice that just received PBS and or empty liposomes. And positive control was 5 fluorouracils. This was the dose, 15 milligrams per kilogram of body weight. And the other 2 groups received either the complex in the free form or in the liposomal formulation at a lower dose, 3 times lower dose of 5 milligrams per kilogram. Here I show you that, of course, the animals were controlled for pain, distress, etc. You can see that in all groups, the animals, the weight did not change much. When in the end, we evaluated the relative tumor volume, I think you can clearly see 2 groups here, this one on top and this one below. These, after 8 days of treatment, the liposomal formulation, which is this one exactly, and no, this is 5-fluorouracil, this is the liposomal formulation of the complex, clearly reduced the tumor size, the relative tumor volume. In terms of average tumor mass, so this was after the end of the study when the animals were executed, we can clearly see that the best results, so the lower average tumor mass was found for the positive control and for the liposomal formulation of our compound. So these are very positive results. We could see an effect from incorporating the compound into the liposomal formulation because the compound is much better when in the liposomal formulation than in the free form. And if we compare the results with the positive controls, we use a much lower dose, 3 times lower, to have more or less the same effect. So this was a positive result. We still did not proceed further with this system. We also studied the other metal complexes. We had interesting results with the ruthenium complex. And in terms of what we can conclude from this study is that this ligand shows high affinity for metal ions and a very versatile coordination. However, one drawback is the solubility of the complexes, which is quite low in aqueous media. The compounds are stable in the presence of albumin. This is important because we know we have albumin in the cell media. So we know that it will keep our complexes in solution. This is important. They cannot precipitate. Both zinc complexes show cytotoxic activity, but low selectivity towards different cancer cell lines. And the drug delivery system was developed to overcome stability and selectivity issues. And the liposomal formulation impaired colon cancer tumor progression in mice and decreased the average mass tumor 2.4 times higher than the free complex and comparable to 5-fluorouracils at a 3-fold lower dosage. So this work has been published in 2 different papers, one dealing with zinc and the other dealing with the other metal complexes. And now I will switch to another system. So this was the system that went further, but since I'm talking about in chronological terms on the evolution of the work. So then we decided to try to get ligands with slightly higher lipophilicity and different groups here. And so basically we obtained 8 different ligands with different substituents here in the para position to the hydrazide group. In this case, These ligands are interesting because, of course, they have two tautomeric forms. We studied this equilibrium in detail, but I have no time to discuss it today. Of course, we characterized the ligands through the usual techniques. We obtained some X-ray structures. We determined the acidity constants and lipophilicity for all the ligands. You can see here the protonation scheme. These were determined by UV visible spectrophotometry because these compounds have low solubility, so we cannot use pH potentiometry. But you can see here the development of the different bands corresponding to the different protonated species. And again, the neutral species is present at physiological pH. And indeed, the lipophilicity is high, but it is lower than in the previous ligand. So, for these ligands, we decided to use two different metal ions. I will speak a little bit about the copper complexes and then the vanadium complexes. Different structures were again proposed for different ligands, and for one of the complexes we could obtain a trimeric structure in the solid state, which we could corroborate that it's also formed in solution. I show you here, for instance, the copper EPR spectra in the DMSO, and they have no resolution. They are typical of species which are interacting with each other. So we study this process by magnetic properties. And of course, we did the aqueous speciation of the copper complexes. We already had the protonation of the ligands, which is essential to characterize the speciation in aqueous solution of the metal species. Again, with spectrophotometry, which yielded the overall binding, the overall stability constants of the different species, which allowed us to modulate the system in different conditions. And we can see that at physiological pH, we have a neutral copper one-to-one complex with the ligands. So this is one of the systems, but they behave quite similarly, although having different substituents. We always need to corroborate the potentiometric studies. We use EPR. This seems a little bit complicated. So this is the low field region of the EPR spectra, which is very informative because it tells us we are supposed to see 4 bands equally spaced due to the hyperfine coupling of the copper electron with the ligand. At some pH values, we see the presence of more than one species, and we can model it. We also use the DFT to propose different binding modes at different pH values. For instance, at pH 2.9, we have a copper coordinated to the 8-hydroxyquinoline, and upon the protonation of this group, different species, so trident 8, are formed at different pH values. We also prepared the oxidovanadium-4 complexes, characterized them by EPR. In the case of vanadium, so for copper, in all the syntheses, we obtained 1-to-1 ligand-to-metal complexes. In the case of vanadium, some systems we obtained 1-to-2. And for vanadium, there is a preference for coordination through the 8-hydroxyquinoline chelate and not through these side groups. We also did the aqueous speciation in this system. It's a little bit more complicated, and these are the EPR spectra that allowed us to propose the binding modes for the different species that we found in the speciation diagram. So this work was quite extensive, many compounds, many techniques. We always evaluate the interaction with BSA. Bovine serum albumin can be considered a model also for the human serum albumin, which is the most abundant protein in blood serum, and it is a transporter of many drugs. So we always evaluate the interaction with bovine serum albumin, and we can see that in the absence of BSA, there is precipitation of the complexes, the vanadium complexes, but in the presence of one equivalent of bovine serum albumin, we can see that the spectra are more or less the same. So the compound is kept in solution. We used also fluorescence emission spectra, in which we titrated the complexes or BSA with increasing amounts of the complexes to determine binding constants. We also used UV visible absorption spectra and CD. You can see here the interaction of the vanadium complex with albumin and the development of a new induction band where the complexes have charge transfer bands. So all these compounds can be transported in blood in the serum by albumin. DNA might be a target for the compounds. We've spoke about this in the last, during this week. So we did studies using melting temperature. So this is DNA alone. This is DNA with one of the copper complexes, a mixture of 1:1. And you can see that there is an increase in the melting temperature, which is indicative of a strong interaction between the compounds and DNA. Fluorescence emission spectra titrations were done in the presence of ethidium bromide, which is an intercalator. We see just a very small decrease in the fluorescence intensity, so we do not believe that these compounds are able to intercalate into DNA. They cannot replace ethidium, which is intercalated into the DNA bases. Something that is also important is to see what happens when we have copper complexes in the presence of glutathione or ascorbic acid, which are present intercellularly. Particularly glutathione is present in a very high concentration, and also ascorbic acid in mammal cells. And we could see the disappearance of the charge transfer band of the complexes. This last spectrum corresponds to the spectrum of the free ligands, so we could conclude that the compounds were reduced from copper 2 to copper 1, and the ligand was released upon interaction with glutathione or ascorbic acid. So the reduction of the complexes seemed to occur in solution. And then I'm not going to show you details. These are many compounds. We evaluated their cytotoxicity in human melanoma cell lines and lung adenocarcinoma, but they were much more cytotoxic towards the melanoma cells. The compounds which showed the best results in the case of vanadium was the fluoride substituted complex, 1:2 metal ratio, and in the case of copper was this one that has a pyridine here. So this is derived from isoniazide, which is a compound that has been applied in different fields as therapeutic. So low IC50 values for these compounds in melanoma cell lines, and we studied the mechanisms of cell death. We could confirm that apoptosis, particularly late apoptosis, was the mechanism of cell death for these compounds, both for the copper and the vanadium complexes. And we confirmed the involvement of reactive oxygen species also in cell studies, particularly for copper, in which a very high increase in the ROS population was observed upon treatment of the compounds with treatment of the melanoma cells with these compounds. So just a few conclusions from this family of compounds. We published the vanadium and the copper systems in these two publications in 22 and 23. So again, these ligands are still quite lipophilic. They are neutral at physiological pH. The metal complexes interact with relevant biomolecules, so they can be transported by albumin, which can also solubilize them in the cell media of these cytotoxicity studies. They interact with DNA, although not by intercalation, and they are able to, the copper complexes are able to react with glutathione or ascorbic acid with reduction to copper 1 and the release of the free ligand. They are cytotoxic, particularly towards the melanoma cells, and redox behavior is relevant for the mechanism of cell death. through the production of ROS, and I didn't show, but we could observe also caspase activation, caspase 3,7, which is an indicator of cell death by apoptosis. So just to conclude, I will briefly show you a third system that we have been working on. So the previous work was work done by a PhD student, Nadia Ribeiro. This is work from Leonor, a postdoc. So in this case, we also used the same aldehyde, the 8-hydroxyquinoline hydrohyde, but we reacted it with amines. And as amines, we chose amines that have morpholine or piperidine moieties. Why? Because these units, when they are present in compounds, in a ligand, they also we can get compounds with good cytotoxic activity. So joining these two units might be a good strategy. For the complex synthesis, we decided to use zinc and copper, and we obtained 1:2 metal to ligand ratio compounds. Of course, all the compounds were characterized by the usual techniques. I will show you just a few of them. So these ligands are Schiff bases. I think some of you know that Schiff bases are prone to hydrolysis, so it's easy for the ligand to revert to its original reactants. And we could observe that this happens with these ligands. So this is the NMR spectra at various pH values in a solution containing 70% of water, 30% of DMSO to solubilize the compounds, and we could identify the peaks belonging to the imine, which decreased with the pH, and the peaks belonging to the aldehydes that increased with time. So these ligands are not so stable, but still we could determine their proton dissociation constants using spectrophotometry, because quite low concentrations are used, and these are fast measurements. And we could obtain the pKa values for the pyridinic nitrogen and for the phenolate. Okay? We could not detect this process because this is not a chromophore, although it can be protonated also. So again, the ligands are neutral at physiological pH. And their lipophilicity is now a bit lower. So these compounds are more water soluble, although not that stable. So next, what we did was to prepare the metal complexes. These systems crystallized quite easily, and we obtained crystal structures for all the complexes. The zinc complexes show octahedral geometry, and the ligand binds the metal by the hydroxyquinoline and also the imine atom. In the case of copper, we obtain two different types of structures, although the coordination to copper in both types of structures occurs through the 8-hydroxyquinoline moiety. But in the case of L1 and L2, we observe the presence of dimers, in which there is an addition coordination through the phenolate of the 8-hydroxyquinoline to copper. So different behavior for the zinc and the copper complexes. So next we study the complexation by aqueous speciation. You can see here the spectra that were measured for one of the zinc systems and the spectra for assigned two different 1:1 and 1:2 species. Here we have the overall stability constants. Of course, we wanted to compare these constants with 8-hydroxyquinoline to see the impact of having an additional binder. And you have here a table that shows derived stability constants for the bis complexes corrected by ligand basicity. And how can we read this? So the higher the intensity of these bars, the lower the stability. So what we could see is that for copper, the complexes are less stable than the 8-hydroxyquinoline ligands. And this makes sense, right? Because The coordination is the same, is through the 8-hydroxyquinoline, and we have a pendant arm that does not participate in coordination. But we can see that the stability of the copper complexes is still higher than the stability of the zinc complexes. But in the case of the zinc complexes, our complexes are more stable than the complexes with 8-hydroxyquinoline because now we have a tridentate ligand. So all of this makes sense. Of course, we studied the complexation. We corroborated it by EPR studies. You have here the EPR measured at different pH values. The figures that I showed you before were focusing only on this region, which is the region which is informative and gives you information on the binding of the compounds to the metal ion. I'm not going to go into any details. This was a very complicated system. So we were not expecting such a complicated system. But we could simulate the spectra corresponding to all the components that were found in solution in the different pH range. Okay, so the next thing that we did, of course, was to evaluate the cytotoxicity of these compounds in vitro. Again, we chose the melanoma cell lines because this project was focused on melanoma. And these are normal cells, human keratinocytes. And we can see that the complexes are always better than the ligands, which is it's the result we look for. Some of the complexes are better than cisplatin, some others not. But the compounds are not selective towards melanoma cell lines, okay? So they are also toxic for the normal cell line. And we could also observe that the copper complexes are more cytotoxic, slightly, than the zinc complexes. So right now what we are doing is we chose one of these copper complexes. We have been incorporating it in liposomes. The good result is that it still retains the cytotoxic activity, and so we are going to proceed to make a study which is quite similar to the one I showed you, although now it will be with melanoma and not with colon cancer. So we expect to have some exciting results from this system. We also formulated the system that I showed you before. We also tried to incorporate one of the copper complexes into the liposomes, but the incorporation efficiency was very low. So we decided to drop that compound and to proceed with this one. I don't have results to show you yet, but I hope I will have in the future. And I will say that we have also prepared with these ligands the vanadium, the nickel, and the iron compounds. So they are being tested in different types of cancer cells. And so I hope to have some interesting results from this system. So to conclude from this part, these ligands have low aqueous solubility and high lipophilicity, being again neutral. The complexes show high structural variety. We could see in the speciation the 1-to-1 and 1-to-2 metal complexes. The copper are more stable than the zinc and also the vanadium because we have data on that also. And the in vitro cell studies show that the complexes have high cytotoxicity towards several cancer cell lines. And the copper complexes are the most, I don't know what I did. Okay. I just have the one slide more, I believe. Okay, it's closed. It will open. Because I cannot finish without the acknowledgements. Sí. ¿Qué? Sí. Ok. Esta no era la última, era casi. Está un poco lento.
Está cargando.
Está cargando, está pensando. So I think I was here exactly. Okay, so this was my last So this was my last scientific slide, let's call it like that. So I hope I've showed you that these systems are important, they are promising. You know, when you talk about things, it seems that everything we do will give a cytotoxic effect. It's not always the case. Sometimes it's disappointing. You prepare compounds and they are not active. And I believe that, and I think this work shows it, the compounds are cytotoxic but not selective towards cancer cells. And so it's important to develop strategies and to take the compounds, to target the compounds to the cancer cells. So, exactly, so we are investing a lot on this field. The work on copper and zinc has been published in organic chemistry, and we are still doing a lot of work with other metal ions. I cannot finish without acknowledging the people involved in this work, so this involves a lot of collaborations. The group of Eva and Edi in Hungary is responsible for the speciation studies. Jada in Turkey did a lot of cytotoxicity studies, as well as Caterina and Manuela in the Faculty of Pharmacy in Lisbon. And this is the group that is responsible for the X-ray structures. Of course, the funding, this is a funded project from the Portuguese Science Foundation, the institutions to which I belong, and of course you for a kind attention, and my collaborators, Nadia Ribeiro and Leonor. So Nadia is responsible for the two first systems, and Leonor is working currently on the last system, and I thank them because they are fantastic researchers. And I thank you for your kind attention. Thank you very much.
Muchas gracias, Isabel.
De nada.
Una linda presentación. Ahora pasamos a las preguntas. Si el público tiene preguntas, pueden preguntar en inglés, español, ya.
Sí. Portugués.
Y en griego.
Y en griego.
En griego.
Yasu.
¿Alguna pregunta? ¿Alguna pregunta?
David?
Yes, I have a couple of questions.
Yes.
And from the third part of your talk, when you were talking about the shift basis ligand,
Yeah.
and in the complexation part for copper complexes versus pH, did you compare that with the, did you do a control with free copper? Because an acid pH, it looks to me a little bit like free copper, and just to neutral
you mean the EPR?
Yeah.
So we cannot really see it easily in the spectrophotometry, but when we do EPR, typically the spectra which we measure at lower pH values, we have the presence of aqueous copper.
like a free copper.
Free copper,
it's not
yes. And then
complexated.
the ligand starts to deprotonate and it starts to bind to the metal, and then we don't have free copper anymore. Although I think that the speciation I showed you here, I'm not sure it was in terms of the metal, it could be in terms of the ligand. You can do the speciations.
And I think it's a bit farther.
It's in the beginning, no?
No, it's in the third part of your
Okay.
talk.
The third system.
Yeah, the third.
So this
Yeah,
is the
system.
second.
The APR.
Yeah.
No,
For instance,
it's a bit farther.
For instance, this one here, at this pH value, 2.9, we have free copper, and we have a first complex species that we assign to this binding mode.
But it's like about 50, I think.
So this one.
Not yet.
Yep. No.
That
this
one.
be-
That one.
Yes.
Yeah. I think
So-
acidic pH, it could be free copper to me.
Yes, it
and-
can. It
Mhm.
is. Most of the times it is. So only in the very low pH range, and depending on the affinity of the metal to the ligand, typically, and this is, ideal. Also, you should start in a range where you have free metals so that you can determine the stability constant for the first species. If you already start with a metal complex, then you don't know where it forms. So typically in the beginning of the speciation, what we have is free copper that then decreases. And here it's quite clear, okay, there is something else already because this is not a pure, no, it's here. 1, 2, yeah, it's probably just free copper, yeah.
Yeah. So, and the other question is related with the first and second part of your talk.
Yeah.
All of those ligands are anionic ligands?
Sorry,
are? Anionic ligands, like non-neutral.
At physiological pH, they are neutral. So if we have that ligand at physiological pH, it will be in the neutral form.
But not the chief base ligands. I'm talking about the first part about zinc, and the second part when you talk about vanadium and copper.
So when you have the vanadium...
At physiological pH, they are non-neutral, or they
are? Yes. The complexes are also neutral at physiological pH when they complex the ligand. So they decrease so the protonation of the ligand in the presence of the metal occurs at much lower pH, and so they bind the metal at lower pH, and at physiological pH you have the complex in which the ligand is neutral. There are other species in other pH ranges which can be protonated or deprotonated, but at the physiological pH they are neutral. This is why they are not so soluble also, because neutral compounds will more easily precipitate in water than if you have a positive or negative charge on the complex. They are more soluble at physiological pH.
Okay, and my last question, I'm sorry. And the first system, the zinc system.
The first
system, zinc.
Yes. Yeah.
Do you have any clue of how that work into the cell? Because that zinc cannot give you the redox properties.
No.
Should it interact with DNA or something like that?
Yes, so I think that in the case of the first complex, many different things might be happening. But the effect can be from the ligand by itself and by zinc participating in some process, non-redox processes, of course, because zinc is not a redox active metal. But yeah, in that system we did not proceed a lot into the mechanisms of action. Okay, so we did mostly cytotoxicity, and then we developed the liposomes and studied further. And due to the very low solubility of the complexes, we decided not to proceed much further with that system. So in terms of mechanism, and I think there is a lot, and we've been speaking about this during this week, there is a lot of knowledge about the way copper and, for instance, iron, they impose cell death, particularly by the generation of reactive oxygen species. In the case of zinc, it is not possible, but zinc is involved in many biological processes, in many, many enzymes. But I cannot say for sure if the effect is from the complex, the zinc complex, or simply the ligand, and metal and ligand go each its own way. So no clear answer on that.
Yeah, thank you.
Thank you.
Thank you very much. Very nice talk.
Thank you.
No, just a comment, because I really enjoyed your talk, because you talk a lot about benzotriazole, and in fact we use that compound as a corrosion inhibitor for copper. Yeah, it's the absorption energy at copper site is quite strong, so you can stop transfer reaction at that site.
Okay.
So great.
I didn't know.
You help me to understand further about the effect of benzotriazole.
Thank you. We had never worked with benzotriazole. It was like a first trial, and I was a bit, because we always draw the molecules in a way, but I mean the chelation system can change. And the problem is that it was really, we couldn't crystallize any of the compounds. We had no X-ray structure. So all the structures that we proposed involved a lot of spectroscopic studies and to see differences between metal ions, and so it was quite interesting. But yeah, the solubility was a drawback. But thank you very much.
Thanks.
¿Alguna pregunta? Isabel.
Yes. Sí.
¿Ustedes han encontrado alguna relación entre la estabilidad del compuesto
Sí.
y la actividad anticancerígena?
No.
Es decir,
Yes.
a lo que voy,
Yes.
¿sabes lo que voy? Porque un compuesto puede ser muy estable y eso significa que no va a reaccionar
Sí.
como nosotros queremos.
See, no, we did try, particularly in the second system when we had many different ligands, we tried to correlate cytotoxicity with a lot of parameters, and we found no correlation. Yeah, but we did try, because we had a lot of different ligands, different electronic properties, and all this. We had stability constants, and yeah, in the end we were like doing a lot of trying to do correlations, and we couldn't correlate anything.
Bien.
A disappointment in that aspect, because it was one of our aims. Why designing so many ligands and preparing so many different ligands, so many small changes? But in fact, in the end, we could not really see a correlation, not with DNA binding, not with, because we tried also with albumin binding, DNA binding, but we couldn't find any correlation, unfortunately.
Bien.
Yes, thank you.
Bien, ¿hay alguna otra pregunta? ¿No? Bueno, le agradecemos a Isabel.
Gracias.
Muchas gracias por haber venido.
So I expect some of you in Lisbon in the next years. Yes.